Okay, welcome back to Real Analysis. Continuing our work in Chapter 8 on the integral, definite integral. In Section 8.3, we're going to continue and achieve one of the, well, crown jewels of any real analysis course, and it's the first form, anyway, of the fundamental theorem of calculus. So this is our first glimpse at the relationship between this notion of derivative that we developed back in Chapter 7 and this integral that we're developing here in Chapter 8. All right, so what is the preamble? In this video, we're just going to kind of state the theorem and try to give a complete proof of it, keeping the video as short as possible, and we can leave most of the discussion for our Zoom meeting. So the preamble is, as usual, we have a couple of real numbers, a and b. A is less than b, and we've got a continuous function on the interval. And then I want to talk about, kind of defining this function on an interval from a to something. An interval, I need to have length. So if you take x to be any number in that interval except for a, then your function is continuous on the interval from a to x, and the interval from a to x still has positive length because x is strictly bigger than a. So we have this definite integral defined on the interval from a to x. Notice here I'm calling the input variable of my function t. Sometimes people call that a dummy variable. In fact, we don't even really need this stuff in the notation, right? This is a number that depends on the function and the two endpoints of this interval. So you can kind of ignore this f of t dt part, but I certainly can't write f of x dx because then x is sort of taking on values between a and x, and that doesn't make sense. So I'm changing my quote unquote dummy variable to be called t. But back to our story, that definite integral exists by Cauchy's theorem because I've got a continuous function on a closed bounded interval. All right, the definite integral is a number, so this gives rise to a new function. I'm going to call that new function capital F. It's defined for every number in the interval from a to b except for at a. And how do I define capital F? Well, it's the value of the definite integral from a to x. All right, I'm going to actually extend that function to be a function on the interval from a to b just by defining capital F of a to be 0. All right, so that's how I can wiggle around because our notion of definite integral required us to be working over an interval with positive length. The interval from a to a doesn't have positive length, but I'll just say the integral from our capital, not the integral, but I'll just define capital F of a to be 0. So we have this new function on the closed interval from a to b, and its value at x, as long as x isn't a, is the integral from a to x of f. Its value at a is defined to be 0. So the following result is usually called the fundamental theorem of calculus. And while it's usually called the fundamental theorem of calculus version 1 or 2, depending on the book you're reading, here we're going to call it version 1. However, our book just calls it differentiation of the indefinite integral. And I just noticed this right now, and it's too late to stop this video. I'm tired and wanted the video ending to, but the author means differentiation of the definite integral, not the indefinite integral. Okay, so what's the preamble? It's what I just set up above. F's continuous on this interval from a to b. We've got this function. Its value at a is by definition 0, and the theorem says that that function is differentiable on a to b. And its derivative is the integrand. It's the function that we're integrating. Capital F prime of x is f of x at every point. Okay, before we define derivatives only at interior points of open intervals, so at a and at b, we're going to be talking about so-called left and right derivatives. And I said those the other way. At b, it's a left derivative. At a, it's a right derivative. It just means that when we take the limit, we'll restrict our variable to one side or the other of the place that we're taking the limit at. So it's really no big deal, although we haven't really emphasized one-sided limits in this particular real analysis course. We'll do it on the fly in this proof. Okay, so I'm going to just try to walk us through the argument and try to keep this as short as possible. So let's pick an x in the interval from a to b, except let's not allow it to be b, and we're going to calculate the so-called right-hand derivative of this function capital F. We're going to show that it's equal to f of x. Okay, so how do we start? Well, our function is continuous at x, little f. It's by hypothesis. So that means given an epsilon, there's some delta neighborhood around x, And I'm going to particularly focus on the right-hand side of it. There's some delta that's positive. I can choose it small enough that I know it stays in the domain of this function, okay? And if you take any input in that delta neighborhood, except I'm requiring it to be bigger than x, so that's why I'm taking this so-called right-hand limit, then the function's values differ from f of x by less than epsilon. And I'm writing that as some inequalities like this. So f of t is at least f of x minus epsilon, but it's no more than f of x plus epsilon, as long as t satisfies this condition, that it's bigger than x, but less than x plus delta. Okay, and I'm going to call that equation 1, because I'm going to refer to it later. So that's by the continuity of our function f. Good. Okay, now the variable that I'm going to take the limit with respect to the derivatives, I'm going to call it h. And I'm going to suppose that it's a positive number, and without loss of generality or for the proof to work, I'm going to take h to be less than delta. We're eventually going to let h go to 0, so it doesn't matter if I start off by assuming it's less than this number delta. Okay, so then I've got 3 intervals. Maybe it's easiest to look at the picture here. So I've got my a, I've got my x, I'm adding delta to x. That's a little bit bigger than x. And then I take this number h, which is between 0 and delta. So x plus h is going to be between x and x plus delta. And then I've got some intervals. I've got an interval from a to x. Oops, sorry, I wasn't watching there. A to x. I've got an interval from a to x plus h. Good. And I've got the in-between interval, x to x plus h. F is continuous on all of those intervals because it's continuous on a to b. So the definite integral exists on all those intervals, and we have that additivity theorem. Okay. So the additivity theorem says that the integral of f from a to x plus h, that is the widest interval, it's equal to the integral of f from a to x, the first subinterval, plus the integral from x to x plus h. Okay, so that's what theorem 8.4 says. And just using our definition, the integral from a to x plus h, well, that's f of x plus h by definition, capital F. The integral from a to x, that's capital F of x, and I've subtracted it to the other side of the equality. And so that difference is equal to this integral from x to x plus h. Good. Okay. But on this interval from x to x plus h, the picture just slid off, but that interval from x to x plus h, it's in our delta neighborhood. So our function satisfies equation 1. That is, for every input in that interval from x to x plus h, the output is at least f of x minus epsilon, but it's no more than f of x plus epsilon. So using the monotone theorem, the order property of integrals, if I integrate f of x minus epsilon, I would get something no more than the integral of f, which would be no more than the integral of f of x plus epsilon. Okay, all on this interval from x to x plus h. So that's using 8.6. You're going to do a homework problem, I'll highlight it in a different color, that says when you integrate a constant function over an interval, first of all, a constant function is continuous, so the integral exists, and the value is that constant function times the width of the interval. Okay, so those outer two integrals, f of x minus epsilon is a constant with respect to t. It's not varying. So the integral of it from x to x plus h is just its constant value times the width of the interval, while the interval from x to x plus h is width h. Okay, I'm just rewriting the integral from x to x plus h in terms of this function capital F. Good. Okay, so now take that line, the line colored green, partially from your homework problem, and let's do the following. Let's divide everything by h. Okay, and then subtract f of x. You get the next line. So we'll get that this difference quotient, capital F of x plus h minus f of x over h, take away little f of x, is at least minus epsilon and no more than epsilon. Or if you rephrase that in terms of absolute values, you get that thing. All right. But epsilon was a positive number that was arbitrarily small. So it follows that if we take the limit as h goes to 0, that inequality written above there shows that we can, that limit is going to be, well, it's an absolute value. It's greater than or equal to 0. But the function that we're taking the limit of is less than or equal to epsilon for any epsilon. So taking the limit as h goes to 0 from the right of that difference, the quantity in the absolute value, I'm talking fast because I want this video to be over, the quantity in the absolute value has to approach 0. But f of x doesn't depend on h, so I can just express that by saying that this difference quotient is equal to f of x. Okay, so in other words, the right-hand derivative, it's right-hand because I'm only taking the limit as h goes to 0 from the right, of capital F of x is little f of x. F prime of x is little f of x, where the prime is denoting the positive derivative. We can just make up some notation here. F prime from the right at x is little f of x. That's the first part of our proof. Okay, so to finish it off, I'm tempted just to say this is an exercise for you, but we just have to argue the same thing from the left. So from the left, we'll take x to be any number, but not a itself. A doesn't have anything on its left in this interval from a to b. Okay, so we're going to argue about the left-hand derivative. So we basically just go through the same steps. I'll go through it kind of quickly, trying not to trip on my tongue. We'll take a positive epsilon. By continuity, there's some delta that if you look at the left side, quote unquote, of the delta neighborhood around x, you can make sure that it's in the interval from a to b. And if you take any input in there, the output is between f minus epsilon and f plus epsilon. F's value at x, I mean. And then you'd take an h that was between minus delta and 0. So notice such an h is less than 0. And then the corresponding intervals that you'd look at are those three. So look at the picture down here. You've got a, the smallest number in the list up there is x minus delta. Then x, notice I'm writing plus h, because again, h is less than 0, right? So when you add h to x, you're going to get something less than x. So those intervals I'm looking at are this time, well, a to x is the big one, a to x plus h, slightly smaller, x plus h to x, the intermediate one. So we use additivity. Additivity says, look at the picture when I say it, the integral from a to x, the biggest interval, is the integral from a to x plus h plus the integral from x plus h to x. That's the additivity theorem. Rewrite that in terms of what capital F is. Okay, a to x is capital F of x. A to x plus h is capital F of x plus h. So we have subtracting again, the difference of those things is that integral. But now applying equation 2 up there, our function satisfies 2 on that interval. So the order property of integrals gives us those three things, right? So just kind of integrate from x plus h to x, if you like, across to equation 2. Use your homework again. So this time I've got the constant function f of x minus epsilon over this interval from x plus h to x. Its width is the opposite of h. Remember, h is less than 0, so the opposite of h is a positive number, so that's the width of that, x minus x plus h. Same thing over here. Constant is f of x plus epsilon times the width. We wrote above that this integral from x plus h to x of f of t is the difference of the capital F's. Okay, now same thing, divide by the opposite of h, it's a positive number, so it's not going to change the inequalities. Subtract f of x, rewrite that thing in terms of absolute values. Okay, epsilon was arbitrary, so if we take the limit as h goes to 0 from the left, h was a negative number between opposite of delta and 0, so taking its limit, we get that the absolute value expression goes to 0, or said another way, that this difference quotient, I skipped over, I guess, a small detail here. Notice that I changed the order of subtraction in the numerator, but I also wrote h in place of minus h. So this fraction and this fraction are algebraically equivalent. So we get that the limit of this thing is equal to f of x. And what does that mean? That means that the left-hand derivative of capital F, making up that notation, is little f of x. Nice. Okay, so we're basically done. We'll just kind of wrap up by saying if x was in the open interval from a to b, then both the arguments above are valid. So we've got the left-hand and the right-hand derivative both exist and are equal to each other. That is, f is differentiable, capital F is differentiable, and its derivative is f of x. All right. If you picked x to be a, then the first argument would show that f has a right derivative and its derivative's value was little f of a. If you pick it to be b, the second argument says it has a left derivative and its left derivative is f of b. And that concludes the proof of the fundamental theorem of calculus. All right.